Oh, all right, now we can get started. The green light came on, so we're good. Now, what I'm going to show you now is when we can get weightless. There is a way to get weightless here within our atmosphere here on Earth, and basically what we do is we do a really steep climb, and then do a dive. All right. Now this is the fancy vomit comet. Where I'm going to show you another one, the weightlessness that can happen, and what happens is the airplane goes into a dive that is greater than the acceleration due to gravity, which we will talk a lot about in this course, of the acceleration due to gravity, which is 9.8 meters per second squared. Okay, well, let me just write that down so you can hear what I'm talking about. All right, so the acceleration due to gravity, this may not mean much to you. Accelerate, we call it G. All right, this is gravity. And it's 9.8 meters per second. So it's per second squared. So every second a body is falling, it'll gain 9.8 meters per second of velocity, which is about 15 miles an hour. And so after 3 seconds, things are falling at about 45. Well, actually, much faster than that. Okay. No, it's the distance that they've gone. So they're picking up because after 3 seconds, they're going 30 meters per second roughly, and so that's almost 60 miles an hour. And we'll look at those conversions too. But anyway, so this is the gravity thing, and on the Vomit Comet, they're going, their acceleration is greater than that on the Vomit Comet. All right, and so therefore it feels, since it's accelerating faster than what the Earth is pulling you down, you float. Okay. All right. And let's just take a look at what that looks like. And this is long before the ASPCA.
In this sequence are shown experiments of simulated weightlessness, or zero-G. To produce this weightless state, an aircraft, in this case a Convair C-131, is flown through a Capillarian trajectory. Starting at 12,000 feet, the aircraft goes into a 10-degree dive until a speed of 250 knots is reached. After a pull-up at 2.5G, a 35-degree climb results in 15 seconds at 0G. The maneuver ends with a 35-degree dive and pull-out at 10,500 feet. In these experiments, you can see the disorientation resulting when an animal is suddenly placed in a weightless state. Cats, when dropped under normal conditions, will invariably rotate their bodies longitudinally in midair and land on their feet. This automatic reflex action is almost completely lost under weightlessness.
Kick that cat up into that post.
Pigeons normally keep their bodies in a horizontal axis while in flight. These zero-G birds have lost their feeling for what is up or down and point in all directions, some even flying upside down.
Okay, so you can be oh, I need to get out of here. There we go. Stop lying, Trump. Well, I don't know if that'll happen or not. Anyway, so kilogram question. If an astronaut has a mass of 100 kilograms on Earth, that's his mass. Now that's how much atoms and molecules he's made up of, or she is made up of. What is the mass on the moon? Where the moon is only 1/6 the force of gravity. So you take 9.8 divided by 6, and that's the acceleration due to gravity on the moon. That's why you can jump. That's why even me, my bulky self can get, I can sky higher than LeBron James can on Earth if I'm on the moon. Maybe. I think I got a 6-inch vertical leap now, so that would give me 6 times. I could go 36, which is about LeBron James's vertical leap. He's right around 32, 34. So yeah, I can jump higher than he can. But my mass, does my mass change? Do I get compressed? Do I add more? Do I get more stuff in me? No. So I think, so what is that going to be? It's going to be the same. So your kilograms, your mass stays the same no matter where you are in the universe. What changes is your weight, depending on the size of the planet or star or non-existent where you're weightless is. Okay? All right, the next thing we're going to look at is the seconds. All right, we're going to look at seconds. And then we'll also look at the meter. Basic unit of the meter, okay? Between 1890 and 1960, the meter was defined using the bar made from an alloy of platinum and uridium, okay? Now it's measured upon how far light travels within this amount of time, which is actually the inverse of the speed of light, okay? Because we know how fast the speed of light is. We've measured that. We've measured it all the way down to here, to this, to here. But we keep it, for our purposes, we go 3.0 times 10 to the 8th meters per second, okay? And that's based on a concept. And I'm going to show you a slide here in a minute on what it means to be based on a concept. And then the basic units of the second used to be to find how long it took the Earth to go around the sun. Well, the Earth is slowing down, so that means that's not a good concept to have, because the Earth is, every time it goes around, it's slowing down just a little bit. What doesn't slow down is an atomic clock. A cesium-133 is always pinging off like hundreds of thousands of these little radiation things that we can keep track of per second. And however many of those reactions it happens in a certain amount of time, we call a second. Okay? And the basic unit is the kilogram, and we'll talk about, and then here's the potential unit of mass. Now, the problem with the kilogram, you'll see, is it's not based on a concept. We like for our units, notice, our base units are all based on concepts. The meter is based on this concept of how far light travels within this amount of time. The second is based on an atomic clock. Okay, the number of reactions that happens in an atomic clock. The kilogram is the one outlier, and we're going to talk about that. And that's the end of this mini lesson. Okay, except for I'm going to have you watch a video, and I'm going to give you questions off this video too. All right, and we're going to do some conversions. So this is the end of the slide portion, but then we're going to do some conversions, and there's going to be questions from this video also that you're going to watch that'll be on your mini lesson. Okay, clear as mud? Good.